Dear guests, welcome to our conference second afternoon sessions, second day. Today we will start Mr. Idris Candan. Welcome our session, Mr. Candan.
Thank you very much. Thank you for having me.
Mr. Candan, please introduce yourself firstly, and then I will show your presentation.
Okay, actually, at the beginning of the video, I did present myself, but if you want, I can do again. I am from Kocaeli University. I have a PhD from Middle East Technical University and University of California, Los Angeles. And my subject, research subject is about the semiconductors, thin films, organic and inorganic actually, flexible electronics and diluted magnetic semiconductors.
Nice area, I think, because I'm a physicist and I am working in film coating and characterizations.
Okay.
So it's interesting for me. I will show you, and I will start now your presentation.
Okay, thank you.
After that, we will ask the questions.
Okay.
See you later.
I will be here. Okay, see you later.
Okay, I think you can see.
Is there a problem? I think maybe
I think the presentation goes seriously.
Okay.
Did you see presentation?
Yeah, I see.
I will start again.
Okay. We cannot see now.
Okay, I will start again. Sorry.
Okay. You share the folder. I think you have to share the video format, video screen.
I have a problem, I think. Mr. Candan, do you have your presentation?
Yes, I have.
Yeah, you can share. You can share.
Okay. Okay. Afternoon. Just a minute.
Hocam, ben Ersin. Hocam paylaşımla ilgili sıkıntı var mı?
Okay, I will start. Good afternoon. My name is Idris.
I am from Kocaeli University, Department of Physics. My research subjects include organic and inorganic thin film solar cells, nanomaterials for flexible electronics, and diluted magnetic semiconductor devices. My presentation title is Morphological Investigation of Polymer Solar Cell Layers using Atomic Force Microscopy and Raman Spectroscopy. This is our outline. First of all, I will give some information about our motivation, and then general information about organic semiconductor, conventional polymer solar cell, inverted polymer solar cell, atomic force microscopy, Raman spectroscopy. And then I will explain our experimental techniques, how to prepare inverted polymer solar cell, and how to characterize thin films in this study. And then I will give our results and discussion, and finally I will give some conclusions. Our motivation is that semiconductors are mainly based on the organic materials such as polymer molecules and oligomer. Most of the elements of organic semiconductors are carbon, hydrogen, and oxygen. They can be synthesized without concerning of the limit of source material. The electrical and chemical properties of the organic semiconductors can be ordered by adjusting the chemical structure of the organic compounds in the infinite combinations. They can be coated with several techniques like spin coating, spraying, or printing process, which are very cheap process. And no need of high temperature or vacuum. Organic semiconductors also have high absorption coefficient, approximately around 10 to 5 per centimeter, and a few hundred nanometers of thin films enough to absorb the photons in the absorption range of materials. The organic materials can be used to build the flexible and semi-transparent solar cell devices. Organic semiconductors-based solar cell, low-cost production, wide application area, and environmental friendly components are expected to be next step in the solar technology. In this work, P3HT and PCBM were used. P3HT is P-type organic semiconductor used as a donor, and it has a gap between HOMO and LUMO level in between 1.7 and 2.1 electron volts. And PCBM is N-type semiconductor used as an acceptor, and it has a gap between HOMO and LUMO level in between 2.48 and 2.85 electron volts. Both P3HT and PCBM polymers are soluble in similar organic solvents like chloroform, chlorobenzene, and toluene, etc. A mixture of P3HT and PCBM is perfect candidate for bulk heterojunction photoactive layers. Now, I would like to give some information about conventional and inverted solar cell devices. The conventional structure made up of a substrate, mainly glass, coated with TCO, generally ITO or FTO, and then a whole transporting layer of PSS and photoactive layer of polymer, and then calcium as a electron collecting contact, and aluminum of top contact. But these calcium and aluminum metals are easily oxidized, and they affect the performance of the conventional solar cell devices. So we have to solve this problem. And when we look what is the differences between conventional solar cell and inverted solar cell structures, the main differences is the change in the position of anode and cathode buffer layer, as you see here. calcium layer is replaced with the metal oxide and P.PSS replaced with the molybdenum trioxide. And the position changed. Electron collected in the metal oxide in the inverted polymer solar cell, but in conventional solar cell, electron collected in the calcium side. And light in the both structure come from the glass side, sides. And stability are significantly increased in the inverted polymer solar cell devices compared to conventional polymer solar cells. Now I would like to give some information about atomic force microscopy. Atomic force microscopy is employed for three-dimensional analysis of surface or two-dimensional analysis. AFM scans the surface of samples with a sharp tip, and a detector identifies the movement of the tip. In this way, the surface topological profile is generated on the computer screen. The obtained raw data are analyzed with a special AFM image analysis program like Division, and so 2D or 3D surface profiles, the surface roughness of samples over the scanned area can be obtained. And here you can see the schematic illustration of the atomic force microscopy. And Raman spectroscopy is a powerful, fast and non-destructive technique, and it used to provide information about vibrational, rotational, and other low frequency mode in the sample. In the Raman spectroscopy, local atom bonding structure is examined by an inelastic interaction of incident photons with transverse or longitudinal modes of the phonon. Raman spectroscopy gives the spectral characteristic of the phonon vibration in the solid material so that it can be used to provide the fingerprint of the molecules. Here you can see the schematic illustration of Raman spectroscopy. Now I would like to give some information about our solar cell structure devices. As you see here, we used a glass substrate, TCO coated glass substrate. We coat metal oxide of zinc oxide. Also titanium dioxide or tin oxide also can be used in this layer. Polymer photoactive layer P3HD PCBM spin coated on top of the metal oxide, and then thermally molybdenum trioxide around 10 nanometers deposited on top of the photoactive layer as a buffer layer, and 100 nanometer silver top electrode was thermally coated from elemental source on top of the molybdenum trioxide. The image of polymer sample width and 4 minutes interval you can see here. And finally, we get this device, solar cell devices. As an experimental techniques for characterization, we used atomic force microscopy and Raman spectroscopy, and current density voltage versus voltage used for checking the solar cell performance. Now I will give some results and discussions about our study. The atomic force microscopy results of the zinc oxide. As you see here, we get three-dimensional image of zinc oxide using spin coating method at the room temperature over the area of 2 micrometer plus 2 micrometer. The average roughness of zinc oxide was found as 1.32 nanometer. The AFM image of zinc oxide thin films indicated that the film has uniform crystalline surface morphology. And here you can see the atomic of the PCBM in 3 dimensions over the scanning area. The relation between device performance and the surface roughness of the films concluded from the morphology study is that the high roughness of the film give higher efficiency devices. Our average roughness is found 2.61 nanometer. The surface roughness of polymer is quite high as expected. And it has a hexagonal width Z structure. Why the primitive cell contains 4 atoms and the potential optical modes are split as lambda optic equal to 1 AA1 and E1 plus 2E2 and plus 2B1. The phonon modes of E2 symmetry are non-polar phonon modes, and E2 LO high mode is associated with the oxygen atoms in the structure, while the E2 TO transverse optic law is related with zinc oxide sublattice. In our measurement, the most intense peak at 437 per centimeter is associated with E2 LO high mode, which is the strongest mode observed in the Raman spectra of the zinc oxide thin film. And the other peaks observed at 330 related to E2 TO and 379 A1 TO and 411 related to A1 TO and 583 related to A1 LO modes. Raman measurements show that produced zinc oxide thin film was polycrystalline structure. And when we look at the Raman spectroscopy of the polymer site P3HD of PCBM, the crystal structure of P3HD has a monoclinic unit cell with this parameter, and it's belong to space group P21C with 2 chains per cell. PCBM has a triclinic unit cell with this parameter due to the crystallization of dichlorobenzene. The blending of P3HD and PCBM has been defined as a triple system consisting of amorphous P3HD, crystalline P3HD, and aggregates of PCBM. And all results show that the most dominant Raman peak of P3HD PCBM mixture at 1444 per centimeter is related to symmetric CC stretching. And the second dominant Raman peak at 1376 respond to the C alpha, C beta scatteral stretch mode. And the other Raman peaks at 724 antisymmetric C alpha S, C alpha inner ring distortion, 1087 related to associated with the CH banding, 1176 symmetric C alpha interring stretching, and 1205 combination of CC stretching and CH stretching modes. And when we look the solar performance of the our devices, we measure the current density and voltage measurement was carried out under the EM15 illumination to measure the photovoltaic performance, which is this device configuration. And we see that our efficiency, power conversion efficiency is around 3.74% and fill factor 66%, and open current voltage is 0.57 volt, and short circuit current is 9.95 milliampere per centimeter square. As a conclude, atomic force microscopy measurements shown that the average roughness of zinc oxide thin film was 1.32 nanometer, and average roughness of the P3H PCBM photoactive layer was 2.61 nanometer. The most intense peak of the zinc oxide thin film at 437 centimeter over 1 is associated with E2 LO high mode, and the Raman spectra of zinc oxide also shown that the sample has E2 mode at 330 and A1 TO mode at 379 and E1 TO mode at 411 and E1 LO at 583 centimeter over -1. The most dominant peak of the P3H PCBM polymer was found at 1444, associated with the symmetric CC stretching, carbon-carbon stretching, and the other modes, carbon alpha, carbon beta scatteral, and antisymmetric carbon C alpha S, C alpha in ring distortion, CH banding, symmetric C alpha interring stretching, and combination of CC stretching and CH stretching were also detected in the Raman spectra of P3H PCBM. The power conversion efficiency of efficiency of inverted polymer solar cell was calculated as 3.74%. The inverted polymer solar cell device exhibited as short circuit current of 9.95, open circuit voltage of 0.47 volt, and fill factor of 66%. And thank you for your attention.
Mr. Jonan, thanks your presentation. And I want to say any question. Do you have any question, dear guests? Any question? I think no, but
okay,
I have to ask because I interested your presentation.
Okay.
I want to ask too that as I know, spin coated is a challenging method. You said our AFM image roughness values at 1.32 nanometer roughness values you have.
Yeah.
So can we say polymer-based coating decreasing the porosity of the films or roughness of the films?
Yeah, absolutely. Yes, you are right. They increase the roughness of the films due to the solution based, and maybe in the solution the particle did not solved properly and homogeneously. That's why maybe in the EMF image we see the roughness, a big roughness actually.
I can say the polymer-based materials is advantageous materials for the quanting.
Yes.
Okay, thank you so much.
Thank you.
And then our new presentation is comes from the Volkan Kılıçlı, but he's now at here, so I will share his presentation. Okay. I will wait a minute. Okay. I think we have some problem for the sharing. Did you see the presentation?
Now we can see.
You can see?
Yes, but now this is the browser. Before that, we did see. We saw that.
I will share again. Sorry.
Share the video program, then I think it will be okay.
I will wait a minute. Sorry. Okay, my screen is calm, and I will find the video. Okay. Sorry about that. I will stop my screen.
We can see now. Dear President.
Can you see the
Yeah,
presentation?
we can see now, but there is no voice.
There is
Without
no voice.
Yeah.
Okay.
modules. Very good fracture toughness and excellent corrosion resistance. Researchers have been investigating. Hello everyone. In this session I am going to present my study which entitled Microstructural Features of Titanium 6 Aluminum 4 Vanadium Alloy produced by vacuum arc remelting from waste chips. This study is experimental study currently under investigation. My master student Dilara Nur Taner is working this topic. Here you are seeing my presentation sequences. First, introduction. Second, aim and scope. Third, experimental studies. Fourth, experimental results. Fifth, concluding remarks. And final, references. Titanium 6 Aluminum 4 Vanadium alloy is a alpha-beta titanium alloy with high strength, weight ratio, and excellent corrosion resistance. It is one of the most widely used alloys in the titanium alloys. It is generally used in a wide variety of applications where low density, high strength, and excellent corrosion resistance is required. Titanium 6 Aluminum 4 Vanadium alloy is widely used in biomedical and aerospace applications due to its high specific strength and elastic modules. Very good fracture toughness and excellent corrosion resistance. Researchers have been investigated the recycling of titanium 6 aluminum 4 vanadium alloy scraps by electron beam melting (EBM), plasma arc melting (PAM), and vacuum arc remelting (VAR). These processes are the general remelting technologies for titanium scraps because they can minimize the oxygen contamination. Another recycling process is hydrogenation and dehydrogenation (HDH), which is a powder metal route. The vacuum arc remelting process is used as a secondary processing for the homogenization of high melting point and oxygen sensitive materials such as superalloys and titanium alloys. Also, vacuum arc remelting process can be used for recycling of titanium 6 aluminum 4 vanadium alloy scraps. The purpose of the present study, microstructural features of vacuum arc remelted waste titanium 6 aluminum 4 vanadium alloy chips have been examined by using an optical microscope, scanning electron microscope, and X-ray diffraction analysis. The cylindrical rod samples of 10 mm diameter of titanium 6 aluminum 4 vanadium alloy were obtained in hot extruded conditions. The chemical composition of the titanium 6 aluminum 4 vanadium alloy given in table 1. The waste chips have been obtained from the Alide machine located in Ankara. Waste titanium aluminum 4 vanadium alloy chips were cleaned in 2 steps. In the first stage, ultrasonic cleaning with hexane was performed to remove the oil, and ultrasonic cleaning and drying were carried out with acetone in the second stage. After washing with acetone, the waste chips were dried in an oven at 100 Celsius for 15 minutes. The cleaned chips placed in the vacuum chamber of vacuum arc remelting instrument. The chamber was vacuumed up to 10 to -3 atm, and the protective atmosphere was provided with 0.25 bar argon gas. The sample was produced by melting and solidifying 3 times by creating an arc with 400 ampere and 20 volts with a tungsten electron, 6 mm tungsten electrode. The sample production steps with the vacuum arc remelting process is given in Fig 2. As you can be seen here, here the vacuum chamber remelting, during remelting, and the our samples produced by vacuum arc remelting. Materials characterization. Samples were cut from the extruded conditions and vacuum arc remelted samples and hot mounted for mechanical grinding, polishing up to 1 micron diamond suspension, and finally etched with Kroll's reagent. Leica DMI 5000M optical microscope and Geol GSM 6060 LV scanning electron microscope was used for the microstructural observation. Electron beam scattering diffraction analysis was performed using a Zeiss Merlin field emission gun scanning electron microscope equipped with EDAX TSL EBSD system and a Hikari EBSD camera. The X-ray diffraction pattern was obtained on a Bruker D8 advanced X-ray diffractometer, and it's operated at 40 kilovolt and 40 milliampere using monochromatic copper K-alpha radiation. The samples were scanned in the 2 theta range of 30 and 90 degrees at the scanning speed of 0.05 degrees minutes. Also, hardness test was conducted in EMCO-test Dravision 200 universal hardness tester with Rockwell C hardness method. 5 different indentations were performed and their mean values were presented. Microstructure of the microstructure of titanium 6 aluminum 4 vanadium alloy provided in figure 8. The microstructure of titanium 6 aluminum 4 vanadium alloy, which is produced by vacuum arc remelting, consisting of needle-like structures due to the rapid solidification. Especially, you are seeing figure 8a and figure 8b. Homogeneous beta phase distribution was observed in the extruded condition, especially you are seeing fig C and D. The EBSD IPF maps of titanium 6 aluminum 4 vanadium samples are given in the figure 9. The ascular structure is clearly seen in the figure 9b. Much finer grains were observed in titanium 6 aluminum 4 vanadium alloy produced by vacuum arc remelting process. The XRD patterns of the titanium 6 aluminum 4 vanadium alloy shown in figure 10. It can be clearly seen from the figure 10. Similar patterns have been obtained both extruded and vacuum arc remelted conditions. The hardness values of samples produced by vacuum arc remelting and extruded titanium 6 aluminum 4 vanadium alloy are given in table 2. As can be seen from the table, the hardness of titanium 6 aluminum 4 vanadium alloy produced by vacuum arc remelting was obtained higher than the extruded condition. The high hardness of titanium 6 aluminum 4 vanadium alloy produced by vacuum arc remelting is attributed to the acicular structure observed in the microstructure and formed as a result of rapid melting and solidification. The extruded hardness is 38.3 and the vacuum arc remelted hardness is 40 Rockwell C. Finally, conclusion. It was observed that the microstructure of the extruded titanium 6 aluminum 4 vanadium alloy is quite uniform, and final dispersed beta phase is homogeneously distributed in the alpha matrix. It was observed that the microstructure of titanium 6 aluminum 4 vanadium alloy produced by vacuum arc remelting consists of the acicular structure due to the rapid solidification. It was determined that the titanium 6 aluminum 4 vanadium alloy produced by vacuum arc remelting and extruded condition have a similar phases according to the XRD patterns. The hardness of titanium 6 aluminum 4 vanadium alloy produced by vacuum arc remelting was obtained higher than the extruded conditions. Here you are seeing my references. Thank you for your listening and thank you for your attention. Have a good conference.
Excuse me, hocam. There is no You are unmuted.
Please stop sharing. And then it will be normal. In upper side. Yeah.
Meryem hocam. Meryem hocam. Hocam.
Sesinizi de açmadınız hocam. Sesiniz yok şu anda.
Meryem hocam lütfen paylaşımı durdurun diye yaparsanız. Sesinizi açın sayın hocam. Mikrofonunuzu açın. Hocam altta ekranınıza gelmiyor şu anda. Tam şey yapmıyor. Yukarıda yeşil yanan bir yer var. Yeşil yanan. O yeşil yanan yerde sağ tarafa tıklayın hocam. Oradan kapatın ekranınızı. Beni yönetici belirleyebiliyor musunuz? Beni yönetici yapın hocam.
Hello again. Sorry about my screen problems. Can you hear me again?
Yes.
Sorry. I'm so sorry about this. My screen gives me some problems. Thank you for your presentation to Mr. Kılıçlı. He is now not here, so I can take the questions about his presentation. And now we will start the new presentation. Presentation ID 134. This presentation will be seen by Uğur Barut. Is he here?
Yes, I'm here.
Hello, Mr. Barut. Welcome to our afternoon session. And can you start?
Okay, I'm starting now.
Thank you so much.
Hello everyone, welcome to my presentation. I'm a PhD student at Yıldırım Beyazıt University at the Department of Metallurgy and Materials Engineering. Today I will talk about microstructural surface and electrochemical properties of electrodeposited nickel-boron boron carbide nanocomposite coatings. Content of my presentation: introduction, aim of study, hard chrome plating, electrodeposition, experimental methods, bed composition and electrodeposition condition, characterization of coatings, result and discussion, microstructural analysis, X-ray diffraction analysis, macro hardness of coatings, and wear mechanism, and finally conclusions. Aim of study: in the study, it is aimed to produce nickel-boron boron carbide nanocomposite coatings produced by electrodeposition, which can increase hardness and wear resistance low cost is to apply and can be successfully applied, and also as an alternative to hard chrome plating, which is used in many engineering fields, but has some disadvantages on human health and environment. Hard chrome plating consists of depositing chrome layer onto metal components using an electrolytic bed. It has been in use since 1940s and is a powerful process. Hard chrome plating is a process that is applied to frictional parts to provide lubricity for protection. Today, hard chrome plating method is mostly used in various engineering applications such as defense industry, gas turbine engine, landing gear, gun barrel, propeller hubs, due to their high hardness, outstanding wear and corrosion resistance, low cost, and excellent decoration. But there are two main reasons to replace the hard chrome plating. The first, problem caused by chromium morphology, and the second, problem caused by hexagonal chrome forming during plating. Problem caused by chromium morphology. The micro and micro crack rough surface of hard chrome plating is shown at different magnification in figure. These cracks affect not only chrome plating but also coated part. Hard chrome plating is often used in applications where the parts are subject to very high wear and thicker chrome layer is required. But excessive thickness results in cracks and larger pore structure in the chrome surface. In the plating bed, chromic acid occurs in the anode. And this chromic acid is hexagonal chromium compound, which is known to be human carcinogen, and the process is quite inefficient, producing large amounts of hydrogen and hydrogen bubbles. When these bubbles rise to the surface, this bubble bursts, throwing fine mist of hexagonal chrome into the air. Electrode deposition process. Electrode deposition process involves passing an electric current between two electrodes immersed in electrolyte. The positive charge electrode is known as the anode, while the negative charge electrode is the cathode. The electrolyte contains electrical charge ions. When an electrical potential is applied between the electrodes, these ions migrate towards the electrode with the opposite charge. The positive charge ions to cathode and negative charge ions to anode. Experimental methods. In the study, copper substrates were used, and these copper substrates were grinded with 240, 400, and 600 silicon carbide grind paper by using metal grinding device respectively. After grinding, they were cleaned with acetone and then were decreased with the pure ethanol solution for 1 minute and cleaned with pure water before coatings. Then, prepared bed solution was treated by ultrasonic homogenizer for 1 hour to ensure that the nanoparticles did not precipitate in the bed and were homogeneously dispersed. And finally, the coating process was carried out. Bed composition and electrode deposition conditions of the coating bed are shown in table. In our study, we used 250 gram per liter nickel sulfate hexahydrate, 1 gram per liter 3-methylamine boron, and 40 gram per liter boric acid, and 0.5, 1, 2, and 5 gram per liter boron carbide, respectively. In the plating bed, nickel sulfate hexahydrate is the main source of nickel ions, and 3-methylamine boron is the main source of boron ions. Boric acid is the pH buffer of the bed solution, and it arranges the hydrogen ion and concentration in the cathode fin. Sodium potassium sulfate is anionic surfactant. It reduces the surface trace and pitting on the surface by facilitating the hydrogen output from cathode. It keeps the nanoparticles suspended in the electrolyte, so it can reduce the internal stress and prevents the crack formation. It has effect of grain refiner. For the study, our working temperature for coating bed is 55 centigrade degree, and mixing of coating bed at about 250 RPM during the process. I use direct current, and average current density in this current type is 3 ampere over decimeter square, and work time is 30 minutes. Characterization of coatings. Surface morphologies of electrodeposit nanocomposite coatings were studied by scanning electron microscope, Hitachi TM 4000 plus. Also, how the grain structure changed under different conditions was examined. The phase and structural analyses were conducted by X-ray diffraction method by using Ilkago Miniflex X-ray generator. The full widths at maximum values of X-ray diffraction were utilized to calculate grain size by using Derbyshire equation. The microhardness of the nanocomposite coatings was calculated by using Vickers microhardness test device, carrying out load of 50 gram for 10 seconds. At least 10 measurements were applied and average values were taken as reference. Result and discussion. The figure 3.1 shows the same SEM image of nickel boron boron carbide nanocomposite coatings A 0.5, B 1, C 2, and D 5 gram per liter boron carbide addition. As the amount of, according to figures, as the amount of boron carbide added to bed composition increased, the surface roughness increased. The main reasons for that is increase in the amount of second phase included in the coating structure, causing an increase in volume on the coating surface. X-ray diffraction analysis. Figure the XRD patterns for nanocomposite coating is shown in figure 3.2. The XRD patterns show typical peaks corresponding to 111 plane of nickel coatings according to GPDS card number. Especially peak intensity in 111 plane in nickel boron alloy coating is higher than other coating. With the addition of graphene, while peak intensity of 111 plane decreases, peak intensity of other planes such as carbon 200, nickel 200, 220, and 311 increases. The peak intensity and width are directly related to microstructure. According to Derbyshire formula, the lowest grain size was measured in the addition of 1 gram per liter boron carbide, while the highest grain size was measured in addition of 5 gram per liter boron carbide. In the addition of second phase addition, with the addition of 1 gram per liter boron carbide, the second phase causes grain refinement by preventing grain growth and creating new nucleation zone. The particles added to bed composition every 1 gram per liter started to agglomerate in some areas. Thus, the grain refining effect could not fulfill its grain refining function completely. Microhardness of coatings. Figure shows the microhardness values of nickel boron alloy coating and nanocomposite coatings. Addition of boron carbide to electrolyte lead to increase in microhardness, but after a certain point, microhardness values decreases because the over addition results in agglomeration. The hardness value was measured to approximately 1,286 hardness Vickers for 1 gram per liter addition of boron carbide, and lowest hardness value, which is 165 hardness Vickers for nickel boron alloy coating produced by direct current. Weir mechanism. Figure 3.5 shows Weir mechanism of nickel boron alloy and nickel boron boron carbide nanocomposite coatings. A nickel boron alloy coating, B 1 gram per liter nickel boron 1 gram per liter boron carbide addition, and C 2 gram per liter boron carbide addition. According to the image in the nickel boron alloy coating, although the predominant weir type was abrasive weir, the elimination was seen as the predominant weir type with the addition of nanoparticles. The reason for that, the formation of micro cracks on the surface due to high temperature and fatigue that occur during the wear, and these cracks progress under the surface and break apart. With the addition of 1 gram per liter boron carbide into the nickel boron bed composition, the amount of abrasion decrease and increase in the amount of wear was observed with the addition of 2 gram per liter boron carbide. This is because the best surface strength is obtained with the addition of 1 gram per liter boron carbide. Conclusions: nickel boron boron carbide nanocomposite coatings containing with different amounts of boron carbide were produced. Nanocomposite exhibits a crystalline structure with the preferred orientation of the nickel 111 plane, which is located at 44 degrees. Also, XRD patterns show the peaks belonging to carbon for the nanocomposite coatings. The presence of boron carbide in the nickel boron matrix facilitates the increases in hardness as well as grain refinement, but after a certain point, microhardness values decrease because the over addition of boron carbide results in agglomeration. The maximum hardness value, which is 1,286 hardness Vickers, is produced with the addition of 1 gram per liter boron carbide. Smaller grain size bring about the increasing micro-hardness of nanocomposite coatings. The higher surface hardness was achieved with the addition of 1 gram per liter boron carbide, and as a result, the lowest wear was observed on the coating surface. Thanks for listening.
Thank you for presentation, Mr. Uğur Barut. Any question? I think we have no any question. Thanks for your presentation again, Mr. Barut.
Thank you.
And I will look at our participants and looking Anwar Katep. Is there here? I think no. So I want to start Mr. Samet Sabahoğlu's presentation. Hello, Mr. Sabahoğlu.
Hello.
Welcome our presentations, afternoon presentations.
Thank you so much.
I know you will present your presentation instead of Mr. Mehmet Hakan Demir because he is interesting our technical sessions, technical problems. So you will start your presentation.
Thank you. Hello everyone. I am Samet Sabahoğlu and I am a master student at İskenderun Technical University. I and my thesis advisor Mehmet Hakan Demir are studying about thermoelastic stability analysis during the solidification process. Today I will present one of our studies which is named of effects of coating properties on the growth instability during the early stage of solidification of pure metals on a coated planar mold. Our outline, I will mention about...
Sorry, Samet, can you share your presentation to the screen?
Okay, sorry.
We can't see.
Okay.
Thank you, thank you.
Firstly, I will talk about the outline of the presentation. I will speak of our motivation and the meaning of the thermoelastic stability during solidification. Then I will show the geometry of the process and talk about our assumptions briefly. I will give our solution procedure and solutions of the problem and then show the obtained results. Finally, I talk about major conclusions of this study and say something about what will we do in the future about this process. During the solidification process, liquid material is started to solidify when its temperature reduced below its melting temperature by heat transfer from its surfaces, which are in contact with surrounding mold. The heat transfer from liquid to mold continues until all liquid mass solidifies. If the process is interrupted and the remaining liquid is drawn away from the process, some periodic variations are observed on the thickness of the solidified shell. The undulatory structures are shown clearly in the pictures. The picture is left side shows these variations on the solidified shell thickness after interrupting the solidification process of the aluminum on the planar mold. The other side, the picture at the right hand side shows the similar undulatory structure when aluminum solidifies in the cylindrical mode. Such uneven undulations are not desirable in the manufacturing because the associated thermal distortions in the solidified shell cause several defaults in the solidified ingot, such as cracks. Undesirable cracks have significant effects on the strength and microscopic structure of the ingot, and according to this quality of the final cast products reduces. This leads to waste extra energy, workforce, raw material, and cost. Our aims in these studies are that investigating the instability mechanism in the solidification process during casting of pure metals and improving our knowledge about this thermoelastic instability mechanism and determining the conditions which eliminate or minimize the profile defects. On the other hand, if the solidification is not interrupted, the periodic variations at the freezing front tends to die out the end of the process, since the conditions at the liquid-solid interface becomes less dependent upon the conditions at the mold shell interface due to increasing of the solidified shell thickness. These non-uniform undulations are occurred as a consequence of the non-uniform heat extraction along the shell mold interface. If the heat extraction across the mold is uniform, the solidified shell is grooved planar to the end of the process. But physically, is it not possible due to occurring thermal and mechanical events during the solidification. Therefore, there is some non-uniformities are added to extraction heat. The liquid material solidified faster on the region where the heat flux increases contrary to the region where the heat flux decreases. This behavior leads to undulatory structure at the moving interface between the liquid and solid phases of the solidified material. At very early stage of the process, the conditions at the freezing front are not affected by the conditions at the shell coating and coating mold interfaces. After a time period, they start to affect each other and the undulations are occurred at the freezing front. Stable growth means that when the small non-uniformities are added to extracting heat flux, the amplitude of the undulation is decreased to zero without increasing during this short time. If the amplitude of the undulation increases in this specific time interval, then this behavior defines the unstable growth. And as mentioned before, when the mean shell thickness reaches sufficient thickness, these relations between the interfaces condition again break off and the undulation decays. The closed loop mechanism of the solidification process is shown in this figure. These are the thermal contact resistance at the shell mold interface due to the surface roughness and the other contaminant films. These thermal contact resistances are changed as a function of the contact pressure. Variation in thermal contact resistance affects the conducted heat flux along this region significantly. The temperature and stress fields in each solid layer associated with non-uniform extraction. Variation in the heat flux leads to change in the temperature and stress fields in the layers. These variations in the stress fields led to the thermal distortions in the layers and the contact pressure at the interface between the layer changes. Again, this affects the thermal contact resistance at this interface. As is seen, the thermal and mechanical problems must be investigated together, and the system behaves like a positive feedback system. Therefore, it may have potential to being unstable. But the contact pressure does not affect the thermal contact resistance because of the absence of coupling effect. The physical model of the solidification process is depicted in the figure, and it consists of liquid and solid phases of solidified material, coating layer, and mold. The amplitudes of sinusoidal surfaces are much less than 1, and the wavelengths of these sinusoidal surfaces. The temperature is prescribed as a constant of the bottom of the mold and is denoted by Tp. O and H symbolized of the thickness of coating layer and the formable mold. The solidified material is assumed to be pure metals, and therefore solidification takes place at a distinct temperature. This assumption allows us to consider a solidification front has a sharp boundary. After a time, the liquid forms a solid shell thickness Sxt. Sxt defines instantaneous position of the freezing front and it consists of the two parts such as S0T and S1T. S0T indicates the mean shell thickness and S1T denotes the amplitude of the developing periodic variation at moving interface due to non-uniform heat extraction. Thermal and mechanical problems are uncoupled at the shell coating and coating mold interfaces. As mentioned in the previous slide, the thermal and mechanical problems must be investigated together. This figure shows the blocks diagram of the uncoupled solidification process. It can be seen from the figure the thermal problem affects the mechanical problem, but mechanical problem does not affect the thermal problem in uncoupled model. This means that the temperature distributions in the solid layer affect the thermal stresses, thermal distortion, and contact pressure, but vice versa. These temperature fields are not affected by the stress fields. Finally, this study extends the previous works by adding the effects of coating layer on the solidification process. Mold coating is one of the most important factors controlling the heat transfer rate, and hence it has very important role on the solidification rate and development of microstructure. These are the assumptions made in this study. The temperature in the liquid region is assumed to be spatially uniform and constant in time. It is equal to melting temperature Tm. No heat flux is transferred from the surfaces other than the bottom of the mold. The thermal diffusivities of the materials are assumed to be infinitely large. The solidified material is assumed to be highly elastic during solidification. No elastic strains can occur at any point in the cast after it is solidified. Solidification process is discussed in two parts as heat induction problem with fast change and determination of stress fields. The interactions of these thermal and mechanical problems are called thermoelastic stability analysis. We will consider these problems individually in the following slides. Firstly, the two-dimensional heat conduction problem with fast change for solidification of pure metals on a deformable sinusoidal coated mold of finite thickness is considered. The superscripts B, C, D denote solidified shell, coating, and mold, respectively. The solution of the fast change problem is very difficult since the location of the solidification is not in a priori must calculate as a part of the solution. Due to the non-nullity of the governing equations, exact analytic solution is found for some limiting case only. In this work, the thermal diffusivities of the materials are assumed to be infinitely large, and this assumption allows us to solve this heat conduction problem analytically, since the Fourier-type heat conduction differential equation is transformed to Laplacian type. The initial condition denotes that a very hot solidified shell on the coating surface at initial time. Epsilon 1 denotes the aspect ratio of the upper surface of coating. Similarly, the same aspect ratios are defined for the both surfaces of the mold. The heat conduction equations are solved for obtaining temperature fields in the solidified shell, coating layer, and mold by using these thermal boundary conditions. Equation 1 states that freezing front is isothermal at the fusion temperature, while 2 defines an energy balance between the heat conducted away from the warming interface into the solidified shell and latent heat released during solidification. Equation 3 and equation 4 state that the heat flux from casting to the coating and coating to the mold must be continuous. Heat flux from the casting to the coating and coating to the mold is moderated by the thermal contact resistance RSC and RCM as described by the boundary conditions. Equations 5 and equation 6 due to presence of air gaps and inclusions of materials of poor conductivity at the interface. And lastly, equation 7 prescribes the boundary condition related to constant temperature of the mold outer surface. If the mold is at uniform temperature, there is clearly one-dimensional solution to the problem in which the solidification float at any given time is defined by straight line, y equal to S0t, and all physical quantities are function of y, t, but are dependent of x. If an x-dependent perturbation is to grow and on this unperturbated or zeroth-order process, its development will be influenced by the instantaneous zeroth-order quantities. As long as the perturbation is small compared with the zeroth-order values, the perturbation will be linear and permits us to use Fourier transformation on x. This leads to reducing the dimensionality of the problem. Since the zeroth and first order problems involve fields varying in only one spatial dimension and time, they are considerably easier to implement and more efficient computationally than a full two-dimensional numerical solution of the solidification problem. Experimental observations indicate that development of solidification front exhibits sensitivity-like perturbations. It is anticipated that this non-uniform shell growth could be a response to a pre-existing non-uniformity in the heat flux drawn from the mold surface. Subscripts 0 and 1 define the X-dependent zeroth order process and first order process. Since the perturbation is sufficient, the small component with the unperturbated process and the other field quantities such as temperature fields and solidification flow are defined in the form of inequalities in equation 1 and equation 2. The new form of temperature field substitutes into heat conduction equations, and then the zeroth and first order heat conduction equations are obtained as like this after the periodic and uniform term are separated. On the other hand, after the separating the heat conduction equations, the thermal boundary conditions are needed to separate for obtaining the solution. Substitutes into heat conduction equations, and then the zeroth and first order heat conduction equation. Can you hear me?
Yes, we can hear you.
Okay, I will continue.
Okay.
For this reason, the temperature fields are expanded in the vicinity of the mean shell thickness for y equal to S0t in the form of Taylor series, since perturbation on the shell thickness S1t is very small compared with the S0t. Then the boundary conditions can then be written by separating periodic and uniform terms and dropping the second and higher order and product terms in the small quantities. I can change the slide. I don't know what's the problem. Okay. Dimensionless presentation. To generalize and simplify the solution, non-dimensional parameters are used in solution of the problems, and you can see they are defined as you can see. The zeroth order temperature fields in the solidified shell, coating layer, and mold, and the mean shell thickness are denoted in equation 1. Equation 2 shows the calculated mean shell thickness. Subject to the governing equations for the first order heat conduction differential equations, we assume general solutions for first order temperature field in the layers as follows, and the coefficients are functions of the other process parameters. Finally, the amplitude of the perturbation on the solidified shell thickness is calculated equation 4. A1 to A50 are the constants which are defined as functions of process parameters without S0 beta and S1 beta. We determine the temperature fields in the solidified shell, coating layer, and the mold in the previous slides. Thermoelastic stresses in the solid layers are dependent of the thermal and mechanical behavior of the system. Obtaining stress fields in the solidified shell, coating layer, and mold necessitate complex calculations, since the material is continually being solidified while the solid is in a deformed state. On the other hand, residual stress is occurred in the final cast product even after the temperature of the casting has been reduced at steady state value. We use linear constitutive model for simplifying the modeling complexity. This model is much idealized condition because when the temperature of a material comes closer to its melting temperature, the yield strength of the material decreases. Thermoelastic stresses in the solidified shell, coating layer, and mold corresponding to non-uniform temperature fields during the solidification are represented equation 1. Sigma P is a particular thermoelastic solution and symbolizes and determining solution depending on temperature distribution, and it does not satisfy the mechanical boundary conditions. Sigma H is the solution of the homogeneous problem without any thermal strains. Homogeneous solution allows us to satisfy the mechanical boundary conditions by providing additional degree of freedom. A particular solution is determined based on the thermoelastic displacement potential, which is obtained depending on the temperature field by using this equation. The stress and displacement components can then be expressed using the following relations in equation 2. The homogeneous solution can be obtained by using Ayres stress function in equation 3. Ayres stress function is determined depending on the mechanical behavior of the system. During the solidification process, liquid material is continuously solidified while the solid material is in deformed state, and all material is liquid phase at the beginning of the solidification. According to this, there is no appropriate initial condition for determining the displacement field. Because of this reason, the strains do not need to satisfy the compatibility equation, and Ayres stress function does not have to be harmonic. Incompatible strains don't change as a function of time, because we assume that there is no inelastic strains can occur at any point of the solid after heat has solidified. Therefore, Ayres stress function is having the following form in the right part of equation 3. The general solution of this equation can be written into two parts, and where Kc1 and Kc2 denote residual stress and instantaneous stable response of the solid to the varying temperature field. The mechanical boundary conditions in the present problem can be written as follows, where P is the constant hydrostatic pressure in the molten metal. The boundary conditions associated with the displacement are written in terms of a time derivative, because there is no reference state for determining displacement. Equations 1a and 1b define that the material is initially solidified under constant hydrostatic pressure. Equation 4b indicates that mold stands on the rigid surface and there is no displacement change are occurred at the bottom of the mold. Due to the sinusoidal form of the temperature fields and heat flux with added perturbation on them, the thermal stress fields and contact pressure at the shell coating and coating node interfaces may be written in the following forms. The magnitude and direction of the contact pressure at the solid coating layer interface are same with the y-directional stress field in the solidified shell at y equals 0, but it has negative sense, which is defined by equation 5. The stress fields and contact pressure are separated two parts and as zeroed at first order quantities by using similar procedure in thermal problem. Similarly, also mechanical boundary conditions are separated by using Taylor series expansion in the vicinity of the zeroth order quantities. At the end of the determination of stress fields in each layer, we obtain a two-dimensional differential equation with a variable coefficients which include the residual stress function and its derivatives with respect to the mean shell thickness. When the problem wherein the thermal and mechanical fields are uncoupled along the mold casting interface, as in the present model has been examined, efforts have focused on the development of the contact pressure perturbation. The zeroth order contact pressure is always equal to the hydrostatic pressure, and it is constant during the process. For this reason, first order part of the contact pressure is more important for investigating groove instability. We anticipate that in practice, at very short times in solidification, like right after the molten metal hits the mold surface, the problem is effectively uncoupled. Hence, the predictions of the present model provide some indication of possible groove instability, particularly in the early stage of the process. We determine the first order contact pressure at the shell coating interface by using this equation and it is calculated as equation, this last equation. The dimensionless forms of these equations are shown below. For obtaining the contact pressure, first we solve the first equation to calculate the residual stress function, and then substitute the second equation, find pressure. For calculating the residual stress function by solving the two-dimensional ordinary differential equation with variable coefficients, we use state space representation since the residual stress function is very stiff. The state variables are defined as equation 1. After that, the first equation is written in the equation 2, where quotation marks show the differential with respect to the mean shell thickness, and coefficients EI are the function of mean shell thickness and other time independent coefficient. The solution of this stiff problem is obtained by using a variable step variable order predictor or corrector algorithm. This figure shows growth of the perturbation in solidified shell thickness as a function of main shell thickness at selected values of coating thickness when system parameters are set as above. The result of the present model for U equal to 0 goes to limiting solution in the previous work. As seen in the figure, the thicker coating decreases the amplitude of the growth perturbation at the solidification front. It can be seen that thicker coating layers leads to the faster decay of this perturbation, and it implies that the time for planar growth will be shorter when the coating becomes thicker. It is also noteworthy that an increase in the mold coating thickness causes stabilizing effect on the growth of the perturbation in the solidified shell regardless of the value of other process parameters. On the other hand, growth perturbation approaches 0 as the time passes for all cases. The reason of this behavior is that the conditions at the freezing front is not affected the conditions of both interfaces between the solid layers when solidified shell becomes thick enough. Figure A, in this figure A shows the variation of growth perturbation at selected values of eta when alpha 1 and alpha 2 are equal to -5. The results show that increase in eta decreases the minimum value reached by perturbation in the solidification front and increases the elapsed time to the decay of the perturbation. It means that decrease in the thermal conductivity ratio of the shell and coating materials causes the more stable growth at the solidification front. Figure B shows the effect of eta on the growth of perturbation for the same process parameters used in figure A, except the value of alpha 1, which is changed from -5 to 5. Similarly, it can be seen that increasing the value of eta increases the amplitude of periodic variation at the solidification front. The perturbation grows faster the four larger values of the thermal conductivity ratio of the coating and shell materials and decreases the 0 more slowly. The results of this figure suggest that the coating material should be selected from materials with a higher thermal conductivity than that of the shell material for considered cases to obtain more uniform growth. And this figure A shows the variation of S1 beta as a function of mean shell thickness of specific eta values when alpha 1 and alpha 2 are equal to 5. It can be seen that the effect of eta on the growth of the perturbation changed depending on its value. In the range of 0.5 less than eta less than 2.5, increasing eta causes decrease in the growth perturbation amplitude. When eta becomes greater than 2.5, however, its effect turns out to be opposite, and increases the amplitude of periodic undulations at the moving interface. These results imply the existence of lower eta 1 and upper eta 2 limits of eta. When when alpha 2 is greater than 0, regardless of the value of alpha 1. Figure B indicates the variation of the absolute value of the maximum amplitude of the perturbation for the same system parameters. For this case, eta 1 and eta 2 are determined as 2.6 and 3.4 respectively. This means that increasing eta up to 2.6 leads to a decrease in the amplitude of the variation at solidification front and induce more uniform growth. The maximum amplitude of this sinusoidal like variation is equal to 1 at the values between 2.6 and 3.4, and the perturbation diminishes asymptotically to 0. It suggests that the coating material's thermal conductivity should be chosen between the values of 2.6 and 3.4 times smaller than that of solidified shell material for preventing uneven shell growth in the solidified front. And this figure shows the variation of maximum values of perturbation in contact pressure as a function of coating thickness for different combination of eta and rho. For the maximum value of perturbation in contact pressure decreases monotonically to a minimum value as thickness of the coating increases for all combinations of eta and rho. These results suggest that selecting rho smaller regardless of value eta will have the stabilizing effect on the proposed stability mechanism. And lastly, this figure demonstrates the variation in contact pressure with the mean shell thickness for selected values of contact resistance at shell coating interface. It can be seen that the increase in thermal contact resistance and this interface causes the reduction in the amplitude of the perturbation in contact pressure. This means that pressure-independent contact resistance at the interface between the solidified shell and coating causes to improve the final cast quality. Also, the analysis show that both thermal contact resistance and the interface between the solid layers have stabilizing effect on the grout instability for all combinations of other process parameters. Now, I want to summarize my conclusions of this study. Increase in coating thickness decreases the amplitude of the perturbation in contact pressure and perturbation at the freezing front. It is suggested that coating should be selected thicker for improving the quality of casting regardless of the materials. A bandwidth is determined for the values of the thermal conductivity, ratio of the shell and coating materials depending on the amplitude ratio upper and lower surface of the mold and values lay in them. This bandwidth led to growth of the perturbation which approached the zero asymptotically. The amplitude ratio between the upper and lower surfaces of the coating layer changes the range of this bandwidth. Moreover, it is observed that the range of bandwidth also changes depending on the other parameters of solidification process. Thermal contact resistance at the interfaces have stabilizing effects on the growth instability for all combinations of process parameters. The future works about this study are listed as follows. The model in which the thermal and mechanical problems are coupled will be investigated. This study is extended by adding the effect of thermal diffusivities of the materials in the future study to analyze the full model of the solidification process during the casting of pure metals. The solidification of an alloy involving the presence of the mushy zone between the solid liquid moving boundaries, another challenging problem for future research. The effect of density change between the solid and liquid phase of shell material is also considered in the future studies. There are some of the references we use for this study. Thank you for attention.
Thank you for your presentation, Mr. Sabahoğlu, and I want to ask any questions for this presentation.
I have one question.
Okay.
Okay, thank you for this nice presentation first, and then I have to ask, on which metals or layers can this solution be applied? Do you have any laboratory experimental study?
Can you hear me? No,
Yeah, I can hear.
Now we are listening you. Mr. Sabahoğlu, can you hear me?
Can I repeat my question?
Mr. Sabahoğlu, do you have technical problem?
Can you hear me? I can take this. Wallah.
We are now listening you, Mr. Sabahoğlu.
Ben duyamıyorum ki ya. Ne oldu ki buna? Hayret bir şey.
Mr. Sabahoğlu, we are listening your voice. We hear you.
Okay.
I think
He's gone.
he's
Yeah.
gone, and maybe we wait 1 minute. It's gonna be here after 1 minute, I think. If he is not come, I will go the other presentation. He is coming. Mr. Sabahoğlu, can you hear me? He's connecting. Mr. Sabahoğlu, can you hear me? Are you there?
Okay, I think he is a connection problem.
Yes, he has a technical problem due to the internet.
Okay, no problem.
He is in the session, but I think he not hear us. So I want to start our next presentation. It's about to its title. I'm looking. This presentation title is Cadmium Oxide Reinforced Silver Based Nanocomposite Coating by Pulsed and PRC Electrodeposition Method, and it will be presented by Dila Coşmuş. Hello, Dila Coşmuş. Are you here? Miss Dila, are you there? I'm seeing you in the session, but I can't hear your voice. Miss Dila, are you there? Okay, we cannot. I'm looking. Your voice is open. I think you check your mute button, I think. Mr. Sabahoğlu, are you there? We have some connection problem, I think. Maybe you can come in our session again. We will wait the re-entering our guests. Mr. Sabahoğlu, are you there? Can you hear us?
Yes, I am here. Sorry, I lost internet connection.
Okay, it's not problem. Mr. Candan asked to you a question. Mr. Candan, are you there?
Yes, I am here.
Please ask your question.
Okay, on which metals or layers can this solution be applied?
Solution layer, which
metals or layers?
aluminum metal.
Aluminum, okay.
Yes.
Do you have any laboratory application?
No. Only mathematical models. No.
Totally pure solution. Okay.
Yes. Yes.
Okay, thank you. Thank you for a nice presentation.
Thank you.
Mr. Sabahoğlu, thanks for your presentation. It's a detailed presentation and good presentation. Thanks for your giving your your works. That's a good presentation. And then I want to start a new presentation, Miss Dila. Please, Sabahoğlu.
Thank you. I said thank you.
Thank you very much. You're welcome. We are waiting Dila Coşmuş. I think she has a connection problem. Now I don't see her, but I wait 1 minute, 1 or 2 minutes, or maybe we'll start her video. So I will wait 2 minutes for re-entering the system. I like the online presentations, not videos, so I want to wait, Miss Dila. Hello again. Hello everybody. We wait Dila Coşmuş, but she is not re-enter the session. So I want to start. She is coming. She is coming. Okay. She is joining us. Hello, Dila. Can you hear me? We can't hear you. In your screen, under the screen, you have mute or unmute. I know you know. Can you check it? Because I saw your microphone is open. Dila, can you hear me? Or you can talk? No, we can't hear you. Okay, understand. If you want, I will show your presentation video. Okay, I will start. Hello, dear guest. I will start the next presentation from Dila Coşmuş. I will share her presentation. You can show the new presentation.
Degree student in Materials Engineering Department. My topic is cadmium oxide reinforced silver-based nanocomposite coating by electrodeposition method. In this presentation, first the background and motivation of this study will be explained, then in introduction and problems in electrical contacts parts, a brief explanation of electrical contacts and two main reasons of contact failure will be clarified. In the continue, the reasons to choose silver and cadmium oxide as matrix and reinforcement material will be explained respectively. In method part, the sample preparation, wave composition, electrodeposition, and characterization details will be expanded. After these, the results and conclusion parts took place. Aim of this work is to produce durable electrical contacts with high stability. Nanocadmium oxide reinforced silver matrix nanocomposites will be coated on copper-based electrical contact buttons using. Aim of this work.
Sorry, I want to ask a question. Can you see the presentation? Okay, I will look. Miss Dila, do you have your presentation video? Can you share this?
Hello everyone, I am Dila Coşmuş and I am a master degree student in Materials Engineering Department. My topic is cadmium oxide reinforced silver-based nanocomposite coating by electrodeposition method. In this presentation, first, the background and motivation of this study will be explained, then in introduction and problems in electrical contacts parts, a brief explanation.
Yardım eder misin?
Hello everyone, I am Dila Coşmuş and I am a master degree student in Materials Engineering Department. My topic is cadmium oxide reinforced silver-based nanocomposite coating by electrodeposition method. In this presentation, first, the background and motivation of this study will be explained, then in introduction and problems in electrical contacts parts, a brief explanation of electrical contacts and two main reasons of contact failure will be clarified. In the continue, the reasons to choose silver and cadmium oxide as matrix and reinforcement material will be explained respectively. In method part, the sample preparation, wave composition, electrodeposition, and characterization details will be expounded. After these, the results and conclusion parts took place. Aim of this work is to produce durable electrical contacts with high stability. Nanocadmium oxide reinforced silver matrix nanocomposites will be coated on copper-based electrical contact buttons using electrodeposition method, which is an economical and easy to apply method. The effect of addition and amount cadmium oxide into electrolyte on microstructural, mechanical, and crystal crystallographic structure of the silver matrix coatings will be examined. The results will be compared with the pure silver depositions. In today's conditions, the electricity is everywhere in our daily lives. Phones, computers, fridges, even automated cars are working due to passage of electricity. In an electrical system, electrical contacts are the key of the operation's safety. Like fire accidents, even crash of an airplane, and therefore loss of lives and economy took place over the years due to contact failure. So it is a subject which must be enhanced due to technological developments. So what is an electrical contact? The electrical contact is an electrical circuit component which is found in electrical switches, relays, and has a function to open or close the circuit. It consists of two co-conductive metals and conducts electric current when the space between them is closed and not when the space is opened. In the past, the current between (1 and 2 amperes and a few hundred amperes was sufficient for electrical systems. Traditional alloys were sufficient at that time. However, today, with the technological developments, the energy requirements increased dramatically. Today, high-power circuits need 106 megaamps. Like nano-electromechanical systems and micro-electromechanical systems, electronic circuits operate with between 10 and 6 microamps. And here you can see the damaging of contact surfaces during operation. There are two main reasons of contact failure: breaking the contact and welding. In breaking the contact, as you can see, first two contact buttons carrying current. While they are separating, contact pressure and contact area decreases, so contact is overheated to the melting point. And this causes occurring a molten bridge between contact surfaces. When this bridge breaks, burst initiates arcing. The arcing persists until the circuit is cleared and breaking the process will be occurred. About the welding problem, you can see from the figure two contact surfaces approaching at first. They are touching and rebounding, but while they are separating, a molten bridge forms. When this bridge is broken, arc forms. In final, when rebounding takes place again, they will be welded due to arcing and increased temperature. And from this table, we can assume the results of this contact failure. The reasons of the fire accidents on different countries are given on the table. The percentages of fires in Istanbul took place in different time intervals. It can be assumed that the fire accidents due to electrical contact is the first or second reason in these countries. And the percentages of electrical contact cannot be underrated. In Istanbul, between 110 and 120 fire accidents exist every day. Therefore, more than 20 fire accidents occur due to electrical contacts every day. If we compare the time intervals, in Istanbul, a noticeable change on fires due to electrical contact can be observed. The developments took place, but also the number of electrical machines or instruments in houses, schools, hospitals, etc. increased significantly. So, increase in technological developments and therefore increased electric source need is the reason of that situation. So, what properties electrical contacts must have to prevent these fire accidents? High arc erosion resistance, high resistance against welding, low contact resistance, good arc moving properties, and high electrical conductivity. In composites, the reinforcement materials are changing the mechanical properties of matrix materials. Therefore, composite materials have been researched for electrical contact applications too. And reasons to prefer composites are low weight, high strength, design flexibility, corrosion resistance, extended service life, and low maintenance. In this study, silver and cadmium oxide are used as matrix and reinforcement materials respectively. Why silver matrix? It is metal with the highest electrical conductivity at room temperature. It has high thermal conductivity, high melting point, high elastic modulus, and good corrosion resistance. And about cadmium oxide, most cadmium produced is electroplated onto steel, iron, copper, brass, and other alloys to protect them from corrosion. Cadmium plating is especially resistant to attack by alkali. Cadmium is physically similar to zinc, but it is denser and softer. The plated cadmium has a smaller grain size than electrozinc coatings, and deposits tend to be more uniform and smooth. Consequently, good protection is afforded by thin coatings of cadmium, and thus, in spite of its high price, it is frequently used for the protection of precision parts. The most important cadmium compound is cadmium oxide. It is a brown powder produced by burning cadmium vapor in air, and it provides a convenient starting material for the production of most other cadmium salts. And here, from this figure, you can see the number of papers and the patents during last 10 years about silver matrix nanocomposites. It is increasing significantly. Here you can see the crystal structure of cadmium oxide. All atoms are in full occupancy. The pink and the red balls are cadmium and oxygen atoms respectively. We have 3 different samples to deposit. From the figure on the left, you can see the dismantling of HTC-X9 model contactor and dismounted of the existing coating through the buttons. These coatings are dismounted with sandpaper. From the figure on the right, you see a cylindrical copper sample. This sample is cutted and dismounted for characterization. After dismounting, clearing with pure water and dried of the samples, the unwanted regions to deposit are painted with nail polish. Here on the table, our deposition BEF components can be observed. Silver nitrate, potassium cyanide, dodecyl sulfate sodium salt, and cadmium oxide with different amounts are used. On the below figure, the electrode deposition setup is shown. During the process, anode, pure silver, loses electron. Silver ions dissolve in BEF. Electron gains at copper cathode and changes to solid silver on the cathode surface. And from the right figure, you can see the direct current graph. 10 milliamperes were applied during the electrode deposition process for 2 hours. And for the characterization of our depositions, we used X-ray diffraction, hardness testing, scanning electron microscopy with electron dispersive spectrometry. And you can see the pure silver coatings on the above figure and nanocomposite coatings on the below figure. From the SEM results, we assumed that the addition of cadmium oxide caused more smooth surface. As you can see on the figure C, the 1 gram per liter cadmium oxide silver nanocomposite coating is the most smooth deposition surface. From this table, we can assume the percentages of cadmium and oxygen. Percentages of cadmium in depositions is increased with the increasing amount of cadmium oxide. From the figure on the right, you can see the EDS results of the pure silver and 1 gram per liter cadmium oxide silver nanocomposite coatings. From this table, we can assume the percentages of cadmium and oxygen. Percentages of cadmium in depositions is increased with the increasing amount of cadmium oxide. From the figure on the right, you can see the EDS results of. As you can see from the XRD results, break reflections were observed and they correspond to 111, 200, 220, 311 and 331 reflections of silver. XRD peaks do not show the corresponding reflections of cadmium oxide due to small amount of reinforcement into the silver matrix. The highest peak is the reflection 111 in this result. The intensities of peaks have changed due to composition. The cadmium oxide reinforcement is caused increasing in 111 peak intensity when pure silver and cadmium oxide silver coatings are compared. Also, cadmium oxide reinforcement is caused increasing in silver 200 peak significantly. And from the right figure, the highest full width half maximum is observed due to finer grain size in 1 gram per liter nanocomposite coatings. This result is confirmed with the 1 gram per liter nanocomposite SEM images. Also, the most shifted 111 peak belongs to 1 gram per liter nanocomposite deposition due to increased hardness and strength. And from the hardness measurements, the XRD and SEM images are confirmed. The hardness value of 1 gram per liter nanocomposite coating is the highest. Also, when pure silver and nanocomposite coatings are compared, it can be clearly seen that the addition of cadmium oxide is increased the hardness. There have been studies about preventing the welding problem on contacts with the cadmium oxide, but these studies have been in micro size. There is no study in nano size. So the aim of this study, which is achieving cadmium oxide reinforced silver-based nanocomposite depositions in nano size, is released successfully. And according to the results, addition of cadmium oxide into silver matrix gave smaller grains, greater strength, and higher hardness. When different compositions of cadmium oxide nanocomposite depositions were compared, 1 gram per liter cadmium oxide silver nanocomposite coating gave finer grain size, more smooth surface, highest full width half maximum for 111 peak, highest 111 peak shift, and therefore highest hardness result. Thank you for listening to me. Are there any questions?
Thanks for presentation, Diler Coşmuş. I know you are there, but you have some sound problem. Now, can you hear us, Miss Dila? Hello. I think it's continue. There is a sound problem. Thanks for your presentation. It's a good work, a good presentation. Anybody want to ask any question to Miss Dila? I think no. So I wanna start new presentation comes from the Osman Safa Çiftçi. Are you there, Osman?
Yeah, I'm here.
Welcome.
Thank you.
We are waiting your presentation.
Okay.
When you want, you start. Please share your presentation to us.
Okay. Can you see the slides?
Yes.
Okay. Now let me start. Hello everyone, good afternoon. My name is Osman Safa Çiftçi, and today I'll be talking about a study that I conducted when I was at the University of Illinois. The topic is feasibility study of a magnetic mirror for optical sensing. And let me start by giving a brief background and what we mean by magnetic mirror. So initially, when we think of a mirror, an optical mirror, what happens is when the optical wave hits a surface, which could be a metal, the magnetic field doesn't undergo any change in terms of its phase. However, the electric field of it undergoes a 180-degree shift. And you could see it on the top left. That's what we think of a mirror, and it basically shifts the electric field component of the incoming optical wave. However, there's another way of achieving high reflectivity, and it's to use so-called magnetic mirror. So it's this similar, but works in a reverse way. So it doesn't change the phase of The electric field, however, it reverses, and for a perfect magnetic mirror, it changes the magnetic field portion by 180 degrees. And why it's important is it offers higher light matter interaction. The first designed magnetic mirrors are used for microwave frequencies. And the idea was to have an easier emission and absorption of microwave frequencies. And on the right bottom, you could see a top view of the first proposed magnetic mirror for microwave frequencies. It's basically hexagonal metal plates. However, we're not worrying about microwave frequencies. My interest is in the optical region. The initial magnetic mirrors in the optical region was proposed using metal structures. And by the way, there is no natural material that has interesting magnetic properties. So we have to artificially tailor the designs ourselves, and that tends to require microfabrication or even nanofabrication. The problem with metal structure is high parasitic loss, so we tend to lose a lot of the optical wave in terms of absorption. But in the last 6 years, all dielectric metasurfaces appeared in the literature. One huge advantage of using a magnetic mirror is its polarization independent. And on the right image, you could see the optical response of a magnetic mirror. You could see two reflection peaks. The one that corresponds to around 7.8 micrometer is due to the electric dipole, and the one that's around 9 micrometer is due to the magnetic dipole. And on the left, you could see the SEM image of the structure. It's tellurium cubic resonators sitting on top of a barium fluoride substrate. And people in the literature say there are possible applications such as efficient thermal radiation sources or to control light matter interactions, as well as optical sensing, for example, biochemicals or polymers of interest. And another brief background on what I mean by optical sensing. It's to use electromagnetic radiation to interact with the analyte of interest and observe the changes in the radiation. And these radiation could be fluorescence-based, reflection-based, refraction-based, or absorption-based. And this is the one, the absorption is the one that we're interested because especially in the optical wavelength region, which is the infrared that I'm interested in, the molecules have intrinsic absorption bands due to vibrational modes. And the state-of-the-art structure for optical sensing is the plasmonic nanoantenna array, and that's tuned for extreme signal localization. And people showed 4 orders of magnitude enhancement. On the top right, you could see a standard plasmonic-based nano antenna. So on top of the substrate, we have the nano antenna. In this case, it's a gold nanobar, and then an analyte covers it completely. And when shooting a light to the analyte and observing the reflected light, at resonance condition, the absorption will increase, so the reflection will decrease, and that will be proportional to the analyte concentration. And of course, the nanoantenna's resonance have to match the analyte's absorption band. And so what is the aim and motivation of this work? What do I want to study this structure? Because we know a nanoantenna array is an established structure for optical sensing for at least 2 decades. We know it's a good structure, and people showed even single molecule sensing. And then recently proposed, and roughly in the last 5 to 6 years, proposed all the electric magnetic mirrors are claimed to be good candidates for optical sensing. But there is no study in the literature that actually shows an optical sensor made out of all the electric magnetic mirror. So my question is that really so? And more precisely, can magnetic mirrors be used as an optical sensor? And maybe the next step is, can they even replace nano antennas? So for that one, I did computational studies to observe the enhancement. And by enhancement, what I mean is compared to a structure that doesn't, that's, for example, a planar case, what is the signal enhancement, the absorption enhancement of the structure. And the chosen figure of merit is the logarithm of the fraction of reflectance from a surface covered with a reference material divided by reflectance for an analyte covered array. And the reference material in this case is basically the same material that has zero absorption in the wavelength range of interest. And this is more or less an established figure of merit to show the enhancement numbers so that we could compare. And the chosen analyte in my case is a polyethylene, since it's well characterized and widely available. And on the right top, you could see the extinction coefficient of polyethylene. And you could see between 6 and 7 micrometers, the extinction coefficient is roughly 2 orders of magnitude. And this is the wavelength range of interest I'd like to shoot for. And in the study, I will be comparing 3 different designs based off the chosen figure of merit. Initial case is 70 nanometer gold film, which is sufficiently thicker than the skin depth, which corresponds to roughly around 25 nanometer in the mid-IR range. So this should not give us any enhancement, but will basically be the baseline for our case. Second one is a plasmonic nano antenna array. This is pretty much the state of the art, and it's 2.35 by 0.18 micrometer rectangle with a 70 nanometer 70 nanometer thick gold in a 4.15 micrometer square unit cell. And the substrate was calcium fluoride. And this is also, again, the same structure that from this paper that I got the figure of merit from. And the magnetic mirror is a 1.15 by 1.15 by 1.2 micrometer cubes made out of telluride in a 3.4 micrometer square unit cell sitting on a barium fluoride substrate. And the coating, the polyethylene coating I chose is only 6 nanometer. So this corresponds to roughly around the thickness of a single protein layer, because I know plasmonic nanoantenna arrays can capture even a single protein layer coating. But let's see if the magnetic mirror can do. But and we already know if the coating is thicker, there will be more absorption, which corresponds to less reflectance and higher figure of merit. Let's start with the planar gold film. The image was taken from the literature that I got the figure of merit from. As you could see, for films less than 50 nanometer thick, no detectable enhancement was shown. And again, the figure, the number we're interested in is the logarithm of the ratio of reflectance of bare planar gold film and divided by reflectance of planar gold film covered with analyte. And I actually did the simulation studies, and I saw a figure of merit of less than 4 times 10 to the minus 6. And here you could see the gold nano antenna or a plasmonic sensor, and on the right you could see the telluride magnetic mirror. This was shown for the resonance conditions with no polymer coating. So this is just the optical response of those 2 different structures. You could see the reflectance top of gold nano antenna corresponds to around 6.8 micrometer, which is also the absorption peak of polyethylene. And on the right, you could see there are two reflection peaks. The left comes from the electric dipole and the right comes from the magnetic dipole. And magnetic dipole is the one that we're interested in. You could see the reflectance peaks match well with the polyethylene's absorption peak. And I haven't shown, but there's no resonance condition for planar gold film, as could be imagined. And in here, and this is the crux of the study, it's the preliminary results of the figure of merit, the enhancement numbers. And on the left, you could see the gold nano antenna. It has, the figure of merit is roughly 4 times 10 to the minus 3. And for teleromagnetic mirror, the peak is around 3 times 10 to the minus 4. The wavelength that the peak is shown corresponds to 6.8 micrometer, more or less, which is expected. But as you could see, magnetic mirror's performance is 1 order of magnitude smaller. And as I shown before, for standard planar gold film, unpatterned gold film, figure of merit is around 10 to the minus 6. So although magnetic mirrors performance is 2 orders of magnitude higher, it's still less, it's still an order of magnitude smaller compared to gold nano antenna array. So in summary, I try to see if a magnetic mirror can be used as an optical sensor, and if so, what could be the advantage is it can be polarization independent. However, it's as opposed to plasmonic antenna sensors, because they have to be polarized along the long edges of the rectangular nanobars. Otherwise, the signal enhancement will not be significant. And the other advantage is there's no metal involved for the magnetic mirrors, since it's all tellurium. However, the disadvantage is an order of magnitude smaller performance compared to state-of-the-art plasmonic sensors. However, this was observed for very thin layers. I know to sense thicker polymers, there are different nanoantenna-based designs available. So it's worth, as a future work, it's worth exploring to compare in case of thicker polymer coatings. And also there are other magnetic mirror designs that was first shown in 2017. Instead of relying on fundamental magnetic dipoles, using higher ordered electric dipoles, people have shown an even higher light matter interaction. So that might be another design that we could use and to compare if it's any better. And with that one, I'd like to acknowledge my PhD advisors and other professors and postdocs that I work with, and of course the funding source. And I could take any questions you might have. And of course, thank you for your attention and time.
Thanks for your presentation, Mr. Safa. I want to ask any question about this presentation. Do you have any question, dear guests? I think no, but I want to talk our chairman, Mr. Ateş. He is here now. Hello, Mr. Ateş. Welcome to our presentation.
Hello, thank you very much. First of all, thank you very much, Osman Sefa, for this nice presentation. And we are happy to host you here from Illinois.
Thank you.
I hope next time physically and virtually we can organize the next conference physically and virtually together, and we can see all the academicians here. Thank you again.
Yeah, thank you so
And
much.
thank you, Chair.
Yeah, thank you for the opportunity.
Okay, thanks for your presentation again. So I want to ask, is Demet Özaydın Gündüz, is there here? Miss Demet, are you there? We are waiting some time and I'm looking the schedule. Miss Demet Özaydın is not here now, so we are giving a break for at I'm looking 5 to 10. We are waiting, so this is a break for us. Can you say something? Do you wanna say something now? Okay, so we will see at 5 to 10 o'clock. See you again. Dear guests, welcome again. We waited the Demet Özaydın Gündüz for her presentation, and now she is not here, so we will share to your presentation comes from the Furkan Türker. We will see his presentation, video presentation. I will start this presentation.
So good morning, everyone. I'm Furkan Türker from Penn State. I'll be giving a talk on nucleation and growth of graphene, alpha molybdenum carbide, vertical heterostructures on liquid copper. So good morning, everyone. I'm Furkan Türker from Penn State. So good morning, everyone. I'm Furkan Türker from Penn State. I'll be giving a talk on nucleation and growth of graphene, alpha molybdenum carbide, vertical heterostructures on liquid copper by chemical vapor deposition method. So this work was done at Tob University during my master's studies. So let's get started. With the discovery of graphene, the number of publications about two-dimensional materials increased dramatically, and this is mainly because these two-dimensional materials of So good morning, everyone. I'm Furkan Türker from Penn State. I'll be giving a talk on nucleation and growth of graphene, alpha molybdenum carbide, vertical heterostructures on liquid copper by chemical vapor deposition method. So this work was done at Tob University during my master's studies. So let's get started. With the discovery of graphene, So good morning, everyone. I'm Furkan Türker from Penn State. I'll be giving a talk on nucleation and growth of graphene, alpha molybdenum carbide, vertical heterostructures on liquid copper by chemical vapor deposition method. So this work was done at Tob University during my master's studies. So let's get started. With the discovery of graphene, the number of publications about two-dimensional materials. So good morning, everyone. I'm Furkan Türker from Penn State. I'll be giving a talk on nucleation and growth of graphene, alpha molybdenum carbide, vertical heterostructures on liquid copper by chemical vapor deposition method. So this work was done at Tob University during my master's studies. So let's get started. With the discovery of graphene, the number of publications about two-dimensional materials increased dramatically. And this is mainly because these two-dimensional materials offer new properties, new physics that is not observable in their three-dimensional counterparts, bulk counterparts. And also, since these materials are layered materials, most of them are layered materials, you can basically stack one 2D material on top of another and discover new properties, new physics, and these are called van der Waals heterostructures. So talking about two-dimensional materials, a new family has joined to two-dimensional materials, which is transition metal carbides, also called MXenes. So the good thing about these materials is that you can synthesize these transition metal carbides with different chemical formula. So therefore, their properties vary a lot. And also you can discover new physics and properties by basically changing the composition. But among them, one of them stepped forward, which is alpha molybdenum carbide. And this is because it has high catalytic activity. Therefore, it can be used in gas sensing or any sensor applications, also hydrogen evaluation reactions. Also, it's a superconductor, so therefore it's a good platform to study the superconductivity in 2D limits. And finally, it's able to change its oxidation state easily, which means like the Gibbs free energy difference between two different states is low. So therefore, it is used in battery and supercapacitor applications. So since this talk will be about the nucleation growth of molybdenum carbide, I want to briefly talk about the synthesis approach that was done in the literature. So there are mainly two methods to synthesize 2D molybdenum carbide, and the first of which is the wet chemistry method, also called MXene method. And this is a top-down method, and so you have a starting precursor, which is called max phase for molybdenum carbide. This is molybdenum gallium carbide. And in this method, since the bond between molybdenum and gallium is metallic, you can basically etch gallium atoms, gallium layers by an acid treatment, and then by a simple sonication or handshaking, you can delaminate the 2D flakes. However, the bad thing is this, these flakes are defective, as you see in on the image on the right hand side, and also they are small in lateral size, and because of the acid treatment, it will have surface functionalities. So because of these three properties, it can be used in battery supercapacitor applications, and also it can be utilized as a filler in nanocomposites to give better strength. So in the other method, the 2D molybdenum carbide can be synthesized by chemical vapor deposition. So in this method, first you have a copper foil on top of a molybdenum foil, and at high temperatures, at about the melting temperature of copper, molybdenum and copper alloy forms. So therefore, molybdenum atoms diffuse to the surface of the copper after the saturation. And if you introduce a carbon precursor such as methane gas, then you can form 2D molybdenum carbide on copper surface. And as it is seen from the TEM image here on the right hand side, it's much less effective than the one synthesized by wet chemistry method, and it is a large area. And also, since there is no acid treatment or wet chemistry method, there is no functionality, surface functionality on its surface. So therefore, it can be used in electronic and magnetic applications, and also it's a good platform to examine the intrinsic properties of 2D molybdenum carbide. So regarding the CVD synthesis of 2D molybdenum carbide, there are basically two parameters that are widely studied in the literature, and the first of which is the effect of copper thickness. So since this copper acts as a valve for the molybdenum diffusion, so by changing the copper thickness, you can play around with the molybdenum species that will be saturated on the copper surface. So in a study, they increased the copper thickness, and then they observed a decrease in the molybdenum carbide crystals. So this is because by increasing the copper thickness, molybdenum species take their time to attach an S-formed molybdenum carbide crystal, and therefore you can grow thermodynamically stable crystals with thinner features. And then the second parameter is the methane flow rate, which is the carbon precursor. And they observed that low methane flow ends up with thicker crystals, while higher methane flow leads to the formation of much thinner molybdenum carbide crystals. And this is because of the graphene formation along with molybdenum carbide on the upper surface for the high flow rate of methane gas. And since this graphene will act as a barrier for the molybdenum diffusion, so again, step-by-step attachment of molybdenum species to an S-formed molybdenum carbide crystal leads to thinner crystals. But the number of studies regarding this CVD synthesis of 2D molybdenum carbide is very less comparing to other crystal growth studies such as TMDs, black phosphorus, or boron nitride, and etc. And also from those studies, we know that reactor pressure matters. So in this study, we examined the background pressure on the growth of molybdenum carbide crystals, and also for the growth of large area molybdenum carbide, the rate limiting step for the growth must be determined. So in this context, the aim of this study is to understand the mechanism of nucleation and growth of 2D molybdenum carbide on copper under different conditions. So similar to the literature, we used molybdenum and copper foils as precursors, and we first cleaned them in acetic acid, diwater, and ethanol sequentially for 10 minutes each. And after that, the copper foil was placed on top of the molybdenum foil, and then it was introduced into the furnace. And the system was heated to 1090 degrees C under hydrogen atmosphere. And since this is higher than the melting temperature of copper, after the copper melts, CH4, the methane gas, was introduced into the CVD chamber with a flow rate of 0.5 SCCM. And at this temperature, for 30 minutes, the molybdenum carbide crystals were grown. And finally, the system was cooled down to the room temperature in 2 hours under hydrogen atmosphere. And according to the literature, under these conditions, with a CH4 to hydrogen flow rate of 1/40, graphene along with molybdenum carbide is supposed to form. And actually, we observed a similar result. So this is an optical microscope image of the S-grown sample, and this one is the this was taken after the oxidation of the sample at 200 degrees C for 5 minutes. And this oxidation was done to see the graphene coverage on copper surface, because in the absence of graphene, the copper was expected to oxidize, while the graphene covered regions were protected from the oxidation. So therefore, this orange color represents the oxidized copper, while the banana color is the graphene covered regions. So therefore, it is actually observable that 2 different crystals are formed under these conditions. One of them is molybdenum carbide on copper, the other is molybdenum carbide on graphene. So this was further confirmed by Raman spectroscopy. So this is the SEM figure of the same sample, and the Raman spectrum taken from the region 1 shows only graphene features, while in the 2 there is no peak at all because it is bare copper, and in the region 2 only molybdenum carbide as expected. And at the region 4, the crystal grown on graphene, we observed graphene and molybdenum carbide keys. So therefore, two different crystals are formed. One of them is on copper, the other is on graphene. And similar to the literature, the molybdenum carbide on graphene is thinner, and also it has regular facets. So since this is already reported result in the literature, as I showed you before, I'll not be talking about this in detail. So before jumping into the effect of processing parameters on the crystal growth, I want to show you an interesting result, which is the inhomogeneous distribution of molybdenum carbide crystals on copper substrate, which is caused by the wetting behavior of the liquid copper on molybdenum substrate. And as you see from the original photograph and also from the optical profilometry of copper, the thickness of the copper on molybdenum is not same for different regions on the copper substrate. So at the center region it is thicker, but at the edges it's thinner, and this leads to inhomogeneous distribution of crystals in terms of morphology, thickness, and size. So what we observed is that at the center region we observed thinner crystals and also hexagonal crystals with smaller size comparing to the ones at the edge region. Here, as you see, the crystal size gets larger when we go from center to the edge, and also their morphology is like dendritic or flower-like shape. And to understand the mechanism of this, we need to examine the diffusion path of most species. So there are basically two different diffusion paths for the molybdenum species, one of which through the center of the copper and the other from the edge of the copper. And since graphene first forms, the A path is not quite possible because of the very high activation energy of diffusion of molybdenum through the graphene interface. So therefore, most of the molybdenum species first diffuse to the surface of the copper and then moves to the center of the substrate. And since this diffusion path is longer for the center, for the crystals formed at the center, the attachment of molybdenum to the S-formed molybdenum carbide crystal occurs slowly, step by step. So therefore, hexagonal crystals, thermodynamically stable, thin crystals form at the center. However, at the edges, we observe kinetically controlled crystals, or like flakes. And therefore, for the consistency of the results, I'll be showing the samples, the crystals that were taken from the center of the substrate. So the next thing that we examined is the effect of reactor pressure on the growth of crystals, and similar to the other crystal growth studies with CVD, we observed a substantial difference at low and high pressure conditions.